Today on Applied Science, I want to talk about engine science. I recently did some fuel system work on my car and thought I would share what I learned. In a four-stroke engine, we have a cylinder and a piston, and the piston comes down, which pulls in an air-fuel mixture, and then when the piston comes back up, that mixture is compressed, the spark plug fires, and all of the fuel is turned into gas products, and it also releases a lot of heat, which raises the pressure in the cylinder, and the pressure pushes the piston down and creates mechanical work for us. So the question becomes, when do we fire the spark plug to get the most efficiency out of this whole system? If we're too early, then the gas will burn before the piston even comes to the top, and that wouldn't be very helpful. Or if we're too late, the piston will already be very far down in the cylinder, and when the gas ignites, there won't be the pressure that it creates won't be as high, and we won't get as much work out of the system. One of the things to keep in mind is that we only get this very high pressure when the gas in this space in the cylinder is at a very high temperature, and it's going to cool down very quickly because it's in contact with the metal walls of the cylinder. So the timing of the spark is actually very critical to getting the most efficiency out of an engine like this. When the engine is spinning quickly, we have to have more advance on the spark timing, and this is because the air-fuel mixture burns at a relatively constant rate. So if the engine is turning quickly, that means the piston is going up and down more quickly, and that means we need to have more advance so that the gas has time to ignite and burn, so that we have that high pressure point right at the correct physical position of the piston. Initially, this was accomplished by putting a centrifugal set of weights into the distributor, so as the engine spun more quickly, the weights would swing out and cause the ignition timing device to move rotationally on the shaft here. So we had a good system where as the engine sped up, the spark would become more advanced. Seems like that's a pretty good solution. However, there's another problem. If the engine is under a high load, meaning that your foot is really into the gas pedal, and we're putting lots of air and lots of fuel into here, with an advanced spark, we might have a problem where the spark goes off at the optimal time to produce the most power. However, instead of burning cleanly, instead of the flame front starting at the spark and advancing through this air-fuel mixture, it might actually proceed too quickly through the air-fuel mixture, and we get something called engine knock or pinging. And this just means that the fuel-air mixture, instead of burning smoothly, is sort of exploding. It's burning too quickly, and this can be very destructive to the engine. So in addition to this centrifugal advance that will change the ignition timing just based on engine speed, we need another ignition control system that will measure how much load the engine is under. And this can be accomplished with a vacuum sensor. Imagine that the throttle valve on this engine is completely open, meaning that your foot is all the way on the gas pedal. The engine won't be able to produce any vacuum because when the piston comes down, this valve, the throttle valve, is wide open, and so there's no way for it to create vacuum. Whereas if your foot is completely off the gas pedal, the throttle plate is mostly closed, so when the piston comes down, it will create the greatest amount of vacuum here. In this diagram of a distributor, you can see the centrifugal advance here and the vacuum advance here, so that we have input from the speed of the engine and also the load that the engine is experiencing. And between these two systems, we can come up with the ideal spark advance. So this was all well and good until we started to have to worry about emissions coming from the tailpipe of the car as well. As it turns out, we get optimum efficiency at this point that's slightly advanced from top dead center, and this means when the piston is all the way at the top of its travel. And unfortunately, the engine produces more emissions when it's running at that optimum efficiency point. So when we burn the gasoline, we have a number of different products, and one of them is carbon monoxide. HC is for hydrocarbons, which is basically unburned fuel. And NOx, NOx, is nitrogen oxide and nitrogen dioxide, so NO and NO2. As you can see, we have a higher nitrogen oxide and hydrocarbon output than we would have if we were at a less advanced timing spot. So as an engine designer, we are having a trade-off here. Either we get the most efficiency, so this means the most gas mileage and also the best power out of the engine, but then it also has higher emissions. So, not wanting to give up engine efficiency or have high tailpipe emissions, another solution was developed around 1980, and that was to put a catalytic converter in the exhaust stream from the engine to the tailpipe. And around that time, they called these three-way catalysts because we want it to do three things. We want it to reduce the nitrogen oxides into nitrogen and oxygen, and we want it to oxidize the hydrocarbons into water and CO2, and we also want it to oxidize carbon monoxide into carbon dioxide. This gets a little tricky if we expect the catalyst to perform reductions and oxidations. It means that the oxygen level in the exhaust stream going into the catalyst must be carefully controlled. If there's too much oxygen, then it will have trouble performing the reduction reaction, and if there's too little oxygen, then it will have trouble performing the oxidation reaction. So the solution is to put an oxygen sensor in the pipe between the engine and the catalyst, and use a computer system to adjust the air-fuel mixture so that we always have the optimum amount of oxygen in the exhaust stream here. However, even that wasn't quite good enough, and so the makers of these catalytic converters added cerium, which acts as sort of an oxygen sponge. And the way the system is designed is it actually purposefully oscillates between too rich and too lean. It's basically adjusting the fuel mixture up and down. And when it's a little overly lean, meaning there's too much oxygen here, the catalyst soaks up that oxygen into the cerium. And then when it goes into the other phase of the cycle, that cerium can release the oxygen and allow the catalyst to perform the other half of the reaction. Modern cars also have an oxygen sensor after the catalytic converter, and it uses this just to make sure that the catalyst is doing its job. So ideally there would be a large amount of oxygen here, relatively, and then the catalyst uses that oxygen to convert all of these unwanted products into. The fuel-air mixture also has an effect on emissions and fuel economy. So in the early days before catalytic converters, you could make the conscious choice to say, well, I'm going to run a little rich and I'll get more torque out of the engine, but I won't be as efficient, so consumption will be higher. The inverse of this would be efficiency, of course. So at the lowest point on the consumption curve is the most efficient operating point for the engine. If we're running way too lean, that means that there's not enough fuel in the cylinder and there will be residual oxygen left. If we're running too rich, that means the carbon monoxide content of the combustion will be higher. As it turns out, the vacuum advance on my car has been broken probably ever since the day I bought it. And we can see this in the emissions test numbers. So when you take your car into a smog station in California, or this part of California, they give you this full printout. And they test the car on a dynamometer running at 15 miles per hour at, I think, 50% engine load, and 25 miles per hour at 20% engine load, or something like that. So in 2012, the NO emissions were quite low, 114 and 320 respectively. And in 2014, after I fixed the vacuum advance, you can see it shot up to 870 and 950. So everything else being the same on the car, most likely, or at least we can see from the CO numbers and the HC numbers that the car was probably running with the same mixture. Just with that one change in spark timing, we actually had a pretty big jump in NO emissions. The test also measures percent CO2, and the reason for that is to check if your exhaust stream is getting diluted. So if the CO2 number is too low, that means that you're injecting fresh air into the exhaust stream and the test is not valid. The oxygen percentage indicates how effective the catalytic converter is working. So if the oxygen concentration is too high, that means that the catalytic converter is not doing its job in converting those undesirable emissions into just CO2. The vacuum spark advance system has a few other quirks to it as well. In a real-world system, the engine vacuum does not connect directly to the spark advance on the distributor. It goes through two valves in this case first. One of the valves is thermally controlled by the temperature of the engine, and the other valve is electronically controlled by the idle speed system. So I mentioned this catalytic converter system, but one of the problems with the catalyst is that it needs to be very hot in order to function properly. And another interesting side effect of changing the spark timing is that it changes the temperature of the exhaust gas leaving the engine. So if the spark is less advanced, meaning later in the cycle, more of that hot gas will escape the engine instead of being transferred into the engine walls because it doesn't have as much time in the combustion chamber. So the purpose of this thermal valve is actually to have a hotter exhaust when the engine is cold, thus heating up the catalytic converter more quickly and reducing the engine emissions more quickly after you started the engine. So even though we don't get the efficiency boost of having the advanced spark timing, it's still better to have the hotter exhaust gas to heat up the catalyst and reduce emissions that way. Next, we have this electronically controlled valve that disables the vacuum spark advance when the car is idling or when your foot is not on the gas pedal at all. There's probably a few reasons for this. One is that with a less advanced spark, the idle will probably be a little smoother. So just from a drivability and sort of comfort standpoint, the car won't bounce around as much at idle when you're waiting at a light. And also, interestingly, in the early days, emissions tests were done not on a dynamometer, but just with a car idling, and then with a car at 2,500 RPM, but under no load. So it's very possible that the engine designers of this car knew that and put the switch here so that we wouldn't have vacuum advance at idle, which is one of the conditions where the car's emissions were tested. And since we saw, we can reduce NOx and HC pretty easily just by knocking the spark timing back a bit. So the purpose of this valve was, a couple of reasons probably, but I'm sure one of them was to help out emissions at idle. Of course, on modern cars, all of this is done electronically. There is no distributor, there's no vacuum advance or anything like that. There's just a bunch of sensors and a computer that controls the fuel and ignition system just based on the input of all of those sensors. Okay, see you next time. Bye.